Hey guys, welcome back to the channel. Week three lab. Last week, going to chem, but whatever, it's chill. So yeah, let's get into it.
This week in lecture, we talked all about atoms. All things you see and touch, from very small to the largest objects in the universe, are made of atoms. This is important for school-age kids to know because kids are naturally inquisitive, and it's important for them to understand that all matter around them is made from super small molecules called atoms. Atoms are made of electrons and protons. When different proton and electron combinations are put together, they create different elements. These elements are shown on the periodic table. When using the grading phenomenon, we are able to observe the unique color spectrums, which allows us to observe the unique wavelengths. Bring back what we learned from lecture to lab. In lab, we are able to have the opportunity to create diffraction grading mount, observe various light sources through it, shine a laser through the grating, and use the proctor to measure the laser path angles. We also use the diffraction grating to identify the neon tubes.
To go into a little more about what the diffraction grating is, it's an arrangement of equally spaced parallel slits that separates white light into its own spectrum of colors because each color's wavelength diffracts at a different angle. Light diffracts or bends when it passes through a narrow opening or around an obstacle. In class today we used this as our diffraction grating. This wave phenomenon causes light to deviate from a straight path, which then leads to wave interference, which is a creation of alternating bands of dark and light color. The angle at which different wavelengths diffract differs, which allows each specific light source to create a spectrum of colors.
So in class, we use our diffraction grating to look at 4 different light sources, which we looked at a neon tube, our phone flash, an LED bulb, and our element. So when we looked at the neon tube, it was red, and when we looked at it and moved it around, there was multiple colors shining off to the left and right. And those colors were red, orange, yellow, and a little bit of green. And then when we did our phone flash, we just set up our phone, and then we used our diffraction grating to look at it, and we saw the colors red, orange, yellow, green, blue, and purple. So we saw the whole rainbow. And then we looked at the LED bulb, which is just the light right next to us on the table, and that was red, orange, yellow, green, blue, and some purple shining off the blue. And then for our element, we saw red, orange, yellow, and purple, and the purple and red and orange were more pigment than the yellow.
To add to our element, we were able to look at the periodic table of spectra to find out that the element that was given to us was argon. We found this out by looking at the arrangements of colors and the differences between how light and dark they were, which helped us narrow down to argon being our element.
Because like we said in the beginning, every single element has a different amount of electrons and protons, which means that they all have a different wavelength, and obviously because of that they show us different colors. So it allows us to lock down what we think the elements could be and kind of give us a better understanding that all of these elements have different equations that go into them, and so they're not all going to appear the same when put into light. Our last experiment was also using our diffraction grating to look at the different wavelengths that we see when we're using different colors. So for example, we used laser pointers, and these laser pointers came in blue, green, and red. And they all had unique wavelengths to them, which was something that we probably didn't really know before the beginning of class. And so this was kind of a tedious process that I don't recommend very many elementary age students to do at all. It stumped all of us for like a pretty good chunk of time. But anywho, we had to figure out what the lambdas were. And so we had to use some of the information given to us already on the board. And so that helped us figure out what the lambdas were. And then we had to figure out what the distance was between each wave. And so to do that equation, we would put in the distance between each dot after it went through the grating. And so for those, we got a different array of answers because obviously the different colors went through the grating different. And so we would do obviously the difference in meters, and then we would divide that by the distance of the entire table that we were working on, because that's how far away we shined our light. And then we would take that number that we got, so our distance between the dots and then our distance from the table, and we would divide that by our distance from the table, and then we would times that number by the Landra that we got on the board, and that would help us find our distance between each wave, because when you look at the waves on a chart, it looks sort of like this, and so we wanted to find that distance between each of them. And so we kind of got between the 1600 mark and 1900 mark for all of our distances between waves, which was pretty, not accurate I want to say, but pretty close to what we should have gotten. And so when we did this, we knew that we should have taken this new number that we got and plugged it into a different equation so that we could find out what our actual nanometers were between each and every single wavelength. And so we would do that by taking our D, which is the 1800, 1900, and 1600, and timesing that by that original distance between the dots on the meter stick, and then dividing that by the distance on our table. And so that gave us, for the blue laser pointer, 394.861 nanometers. For the green, we got 498.132 nanometers. And then finally for the red, we got 704.674 nanometers. And so this is pretty accurate to what we saw visually on the meter stick, which we will include a picture of. And so since the red had a bigger wavelength, like distance between each wavelength, it was more spread out on the meter stick. And since the blue had the smallest distance, it was obviously very close in comparison to what the red was. And so this kind of was able to show us like a visual of how colors have different wavelengths, and like we were able to see that in real life. And so I think that would be like not only like educational for students to do, but using these were very fun, and like we were able to see a different array of colors all throughout the entire room. And at nighttime we looked through a fish tank, and that was honestly beautiful. And we looked through different lights, like cascading lights, and that was amazing too. And so it was just kind of cool to see how all of the light in the rooms around us have different wavelengths and are working so milliscopically that we can't even see. So it was nice to kind of be able to appreciate that a little bit. So yeah, thanks for watching, guys.
Thanks for watching.
Thank you.
Love ya.